In this practice problem, we're going to work on problem number 8 from the nuclear reactions worksheet. And in this problem, we are looking for the amount of time required for 70% of a given sample of thorium-227 to decay. And so here we're going to be using our decay equation, which is N equals the original number of atoms, molecules, whatever, times e to the negative lambda t. N is the number or the amount of the sample left, N sub 0 is the original amount, lambda is the decay constant, and t is the time. So initially we're looking for the time. We're looking for how much time it takes for this amount to decay. And we're given the decay constant in terms of the half-life. So one of the first things we have to do here is find the decay constant of the sample. And from our notes and in the data booklet, we know that the half-life is equal to the natural log of 2 divided by the decay constant, which, if we do a little rearrangement, multiply both sides by lambda, divide both sides by t to the 1/2, we get the decay constant equal to the natural log of 2 divided by the half-life. And so if we plug our half-life in, natural log of 2 over 18.2 days. And it's important to realize here that with this equation, the decay constant is going to be in whatever units the half-life is in. And so if your half-life is in days, then your decay constant is going to be in decays per day. If it's in weeks, months, years, whatever the units there, that's what the units on your decay constant are going to be. So you don't necessarily have to change the units if everything is in the same units of time. When we multiply that through, when we calculate that out, we get the decay constant equal to 0.038,38085 decays per day. Okay. So now we can take this and we can plug it in up here. Well, there we go. And for our decay constant, but we have to address everything else. We're not given any original amount of sample. We're not given how much we end up with. We're given the fraction. We're left with 0.7 of what we started. Excuse me, 0.7 has decayed, so we're left with 0.3 of what we started. And so if we put n in terms of n sub 0, we have 0.3 n sub 0. Basically 30% of what we started with equals n sub 0 e to the negative lambda t. And we can see here then that our n sub 0's cancel out, and we're left with 0.3 equals e to the negative lambda times the time. Well, this isn't really in a format we want to use yet. We want to get rid of this e. We want to get rid of this right here. And so just like with any type of algebra, we have to use opposite operation, which in this case is natural log. And so we're going to take the natural log of both sides, which is going to cancel these out. And so we're left then with the natural log of 0.3 equals negative lambda times the time. We're looking for the time, so again we'll do a little rearrangement. And we're left with time equals natural log of 0.3 over negative lambda. Natural log of 3 is negative 1.20, we'll just say 4 because we're running out of room on the side, divided by our negative lambda. So we have negative 0.03805. And so when we multiply that out, we get the total amount of time equal to 31.6 days which we can round to 32 if we wanted to. But there's your final answer.